This meeting is being recorded.
For problem 13 in chapter 7, we are asked to take a look at these following compounds and determine which, if any, of the lone pairs are participating in aromaticity. So let's check out compound A here. And we would say that one of these lone pairs would have to occupy a p orbital to consider this an aromatic compound to have 6 pi electrons. So we would have 2, 4, 6 if we have this p orbital with that lone pair there. And the other lone pair would occupy an sp2 hybridized orbital. So one of these in the plane of the ring, and the other one would be extending outside of the ring. All right, we'll try to represent that. The same thing we would see with this second compound here. One of the lone pairs would occupy a p orbital, and thereby rendering this compound aromatic. So this one would be aromatic, and also this one would be as well. So again, the other lone pair would occupy an sp2 hybridized orbital and extend away from the ring. So one would contribute. So we have one pair here, one pair here. Let's take a look at compound C next. If a lone pair were to occupy a p orbital, then we would have a continuous system of those overlapping p orbitals, right? So if that lone pair were in a p orbital, but we would have 4n pi electrons, right? We have 8 total here. So that's not a Huckel's number. So therefore, we would have an anti-aromatic compound. And to avoid the increased instability associated with anti-aromaticity, the lone pair would be expected to occupy an sp3 hybridized orbital in this case. Oh, just the lone pair. Let's take a look at compound D. So now we have the sulfur. So one of the lone pairs on the sulfur atom would occupy a p orbital, and that would generate a continuous overlap of p orbitals. The lone pair on the nitrogen, this would occupy an sp2 hybridized orbital, and therefore not contribute to the aromaticity of the ring, because this nitrogen atom is already involved in this pi bond here, which is establishing the aromaticity. So only one here in compound D. And then we have compound E shown here, where there is only one lone pair on the oxygen, and it is already participating in aromaticity. And I'm sorry, and it is not participating in aromaticity because the oxygen atom, again, has this, just like the nitrogen next door, has that pi bond there that's already participating in aromaticity. So we would say none here. Then in compound F, we look at each of these nitrogens, which has a lone pair. Neither of these, so we would say none over here, are participating in aromaticity because we already have because we already have the p orbitals, right, established here that are involved in aromaticity. So none of the lone pairs are involved, but the compound is overall aromatic. All right, so these last two structures, we see the compound would not be aromatic because to achieve this continuous system of overlapping p orbitals, each oxygen would need to contribute a lone pair, right, in a p orbital. And if we did that, then we would have 8 pi electrons, which are not a Huckel's number. So this, again, would not be an aromatic compound. And our last structure here, one of the lone pairs on the oxygen could occupy a p orbital, and the other would not, would occupy the sp2. I'm sorry, on the nitrogen, we would have this lone pair occupying an sp2 hybridized orbital that is outside of the ring. So only one of the oxygen lone pairs would be involved in establishing aromaticity.